In this presentation, we are going to look into derivation of Michaelis Menten equation. Michaelis Menten equation is the simplest model that explains properties or activity, mechanism of action of many but not all enzymes. It explains mechanism of action or kinetics of simple enzymes, enzymes that are not regulated. But since it's the simplest model, that's the one that is good to start study of enzymes with. So according to this model, an enzyme-substrate complex is necessary intermediate and all the steps are reversible. So enzyme reacts with the substrate and reaction is reversible to form enzyme-substrate complex. Rate constant for the forward reaction is K1 and for reverse reaction K-1. In the next step, enzyme-substrate complex dissociates into enzyme and product. So reaction occurs and dissociation into enzyme and product. Rates for the second step are K2 and for the reverse second step K-2. So both steps are reversible. Now in general, to study reaction mechanisms of reversible reactions, we apply method of initial rates. So for any reaction, amount of product increases with time until the equilibrium is reached. So starting material substrate is converted into product with a rate of K1. Once the product appears, a reverse reaction occurs with a rate of K-1. Now, because both forward and reverse reaction occur at the same time, it is difficult to actually determine the rate of the forward reaction. So what we do is we plot the concentration of the product as a function of time. And now when we plot the amount of product, we can see that it increases in time. But this curve reflects concentration, and that's a consequence of both forward and reverse reaction. To determine rate of forward reaction only, we have to consider rate at the time when no product is present. Because then, if there is no product, then reverse reaction is not possible. And that's at time 0. And to determine rate at time 0, we simply draw an asymptote at time 0, and that shows us that that straight line indicates reaction rate at time 0. And then we repeat that process for different concentrations of substrate. So we increase the concentration of substrate and again determine initial rate or rate at time 0. And again, doing it, do several different curves like this. So that's the method of initial rates to determine reaction rate for the forward reaction. To determine enzyme kinetics and derive Michaelis Menten equation, we apply the steady state assumption, and soon you will see what it is. So according to Michaelis Menten equation, or Michaelis Menten model for enzyme kinetics, we have two-step reaction in simplest case. So enzyme reacts with substrate in the first reversible step to give enzyme-substrate complex, and in the second reversible step, enzyme-substrate complex is converted to enzyme-product complex, which then dissociates to enzyme and product. If time is 0, so we determine initial rate, then there can be no reverse reaction since no product is formed. That means that K-2 is 0. But other reactions are still occurring, which means that first reversible step is still occurring because that's the step to form the intermediate, the enzyme-substrate complex. So this step is still reversible, and then for the second step, only K2 constant applies because there is no reversible reaction. There is no product. So what we can do is we can plot rate, initial rate at time 0 for various substrate concentrations. So we plot on x-axis substrate concentration and reaction rate, V, on y-axis. So we can determine a maximum reaction rate, although it's approached asymptotically, as you can see, with increase in concentration, so we cannot make exactly accurate determination. How to make accurate determination you will learn in the next lecture, not in this one. In this one, we are only deriving Michaelis Menten equation. And on this graph, I want to emphasize one other important point or important quantities, and that's Vmax half, 1/2 of maximum reaction rate, because that one corresponds to Michaelis constant, Km. You will soon see what Km is. So we want to derive an expression that relates rate of catalysis to the concentration of the substrate and the rates of individual steps. So initial rate equals constant K2 multiplied by concentration of enzyme-substrate complex. So that's the equation actually for the rate of the second step. Now expression for rate of formation of enzyme-substrate complex is K1 multiplied by concentrations of enzyme and substrate. Since that step is reversible, we also need to consider equation for reaction rate of breakdown of enzyme-substrate complex, and enzyme-substrate complex is used up or broken down in two processes, in two steps, either in reverse step, where enzyme-substrate complex reverts back to enzyme and substrate, or in the second step, where enzyme-substrate complex is converted to enzyme and product. So overall rate for breakdown of enzyme-substrate complex is K-1 plus K2 multiplied by concentration of enzyme-substrate complex. And here is the steady state assumption that is very important for derivation of Michaelis Menten equation. Steady state assumption is that concentration of enzyme-substrate complex is constant. If that's the case, that means that rate of formation of enzyme-substrate complex equals rate of breakdown of enzyme-substrate complex. And so when we replace appropriate equations for rate of formation and rate of breakdown, we end up with this equation that K1 multiplied by concentration of K1 multiplied by concentration of enzyme and concentration of substrate equals K-1 plus K2 multiplied by concentration of enzyme substrate complex. And if we rearrange that to get concentrations on one side and constants on the other, we obtain this equation. So you can see on the left, we have concentrations of enzyme and substrate divided by concentration of enzyme substrate complex, and on the right are three rate constants for the two steps. Since we have three constants, we can replace those three constants with a new constant, and that's Michaelis constant Km. So from that graph where you have seen that Km corresponds to concentration at which reaction rate is 1/2 of the maximum reaction rate, now you can see what Km also means. It's a constant that is derived from three constants for the individual two steps. And so when we replace that into the equation, we end up with concentration of enzyme multiplied by concentration of substrate divided by concentration of enzyme substrate complex equals Michaelis constant. Or if we rearrange that equation a little bit, we end up with concentration of enzyme substrate complex equals concentration of enzyme multiplied by concentration of substrate divided by Michaelis constant. Now, there is question, what is the concentration of substrate? Because if substrate is undergoing a reaction, then some of the substrate is used up. But since this is initial rate, product is actually not formed yet. It just began to form, it's time 0. So not much of the substrate is used up. Pretty much the only substrate that is used up is in the form of enzyme-substrate complex. But because the concentration of enzyme is low compared to concentration of substrate, we can assume that concentration of free substrate equals total concentration of substrate. And since we know how much substrate has been put into the reaction, then we know concentration of substrate. And the same, we know concentration of enzyme. What we don't know is concentration of enzyme substrate complex. So if we solve this equation for, or actually, sorry, if we free enzyme equals total concentration of enzyme minus enzyme substrate complex, and that one actually concentration of free enzyme cannot equal total concentration of enzyme because concentration of enzyme substrate complex is substantial compared to initial concentration of the enzyme. So when we replace those quantities into initial expression for the enzyme concentration of enzyme substrate complex, we obtain this equation. And then when we solve that for enzyme substrate, then equation is a little bit rearranged, as you can see, or we can simplify that a little bit. And then in this equation, we can substitute expression for the rate of the second step, initial rate of the second step, which is K2 multiplied by concentration of enzyme substrate complex. And so we get equation that expresses initial rate. Now Vmax is attained when a concentration of enzyme substrate complex equals total concentration of enzyme. In other words, when enzyme is completely saturated. So that means that Vmax equals K2 multiplied by total concentration of enzyme. And when we substitute that into the previous equation, we obtain Michaelis Menten equation. So Michaelis Menten equation is initial rate V0 equals Vmax multiplied by concentration of substrate divided by concentration of substrate plus Km. Now at low substrate concentrations, then Km concentration of substrate is much lower compared to Km. And then we can simplify this equation. So initial rate equals Vmax over Km multiplied by concentration of substrate. Simply we can ignore concentration of substrate plus Km. We can ignore in that factor concentration of substrate. So it's only Vmax over Km multiplied by concentration of substrate. That applies only if concentration of substrate is much lower than Km. So in this case, you can see that reaction is first order with respect to S. Now, at high substrate concentrations, then concentration of substrate is considerably higher compared to Km. And then reaction is actually zero order. So this completes our lecture on derivation of Michaelis Menten equation.